So thanks for Trulia for hosting this. This is an awesome space. And so today we're going to talk about sort of mining data with Apache Spark. And can I get a show of hands? How many of you have heard of Spark before today? The guy put up, yeah. How many of you have programmed Spark? A handful. And how many of you sort of use maybe Hadoop and MapReduce day to day in a way? About half. Cool. And how many of you call yourself engineers? How many of you code? I saw a couple people put down their hands from last year. All right, so let's get started. So actually, I brought a colleague of mine today, Aaron Davidson, who's going to be doing a demo today. And let me introduce maybe myself first. So I was a PhD student from UC Berkeley AmLab, where Spark and Shark and some of the other systems were born. And I used to put a quote around the on leave part of the slide. And one day I got an email from my advisor, and I decided to take the quote out of it. So it's no longer a PhD quote on leave. So I've sort of co-founded Databricks last year with a bunch of other guys, including sort of a lot of the core committers of Spark. And Aaron here is also an engineer at Databricks who's been pretty instrumental in the latest releases of Spark. And he's going to be doing a demo. So for those of you who have seen the introductory Spark talk, the first half of it might be a little bit too introductory for you. But the second part of it, we're going to be doing this demo that's only done, I think, second time in history. The first time was done was yesterday at Hadoop Summit. And a lot of people couldn't even get into the room to see it. That's what Aaron's going to be doing. It's a $2,000 demo. You have to pay $2,000 to see it yesterday. So I'll first talk about Spark, and then sort of walk very quickly through some high-level libraries on top of Spark, and why sort of what the buzz is about. And then Aaron's going to be doing the demo. So before we get into Spark, maybe let's think about what, since the name of the meetup group is called Data Mining, I actually wrote down sort of what I think might match a typical data mining workflow from a day-to-day sort of data scientists or data engineers. So often, what you would do is probably get some data set to your local laptop for analysis. And this data set could be, maybe it used to be very large, for example, production logs from stored in HDFS or stored in S3, or maybe from a live production database. You get like a snapshot sample of the data out. And then you might have to clean it to fill in missing values, to transform the data, slice and dice it, explore, understand some characteristics of the data. And this is sort of, I just put some of the tools you might be using, for example, SQLite, Pandas, R, and then maybe you want to build actually a model on top of this data so you can use it to predict something else. And then you probably what you were using might be scikit-learn, or R itself is an excellent trainer. And then you prototype it, you got your model on some smallest amount of data, and you got pretty good results. At some point, you might have to iterate a few more times. And then once you build this nice model, you want to scale it out to a real data set. And this is where really a lot of the pain point come from, between 3 and 4. Because it becomes, there's actually almost inherent mismatch between what you do on a single node versus what you do on a large cluster. And for example, specific models might work very well on a small data, say in scikit-learn or in R, but once you run that similar model in Apache Mahal, it might not work anymore. And then for some more adventurous or more bleeding edge types, you might want to actually apply your model in real time in a more streaming fashion. And this just gets, at some point, maybe infeasible. So somewhere between like 3 and 4 and 5 is really a lot of the difficulties are. And so we made up this slide a while ago about like the dirty secret, the little dirty secret of big data right now. How do you scale model out? How do you scale analysis out? And really, when you're mining big data, majority of the programmer's time spent fighting sort of with confusing and broken APIs in a lot of the large systems. Sometimes Spark's also part of the cost. And a lot of the machine time is actually spent in moving data from one place to another and then cleaning them. So this actually leaves huge room for improvement. And you can probably see where I'm going next, which is Spark. So let me introduce Spark now and give a more, so my interpretation of what Spark means to me and to some of the data scientists and data engineers. Spark is a cluster compute engine that make it easy easier, at least, to handle a wide range of different workloads. And this includes SQL, like analysis, exploratory analysis. This includes ETL, data cleaning, and this includes machine learning, as well as data streaming. So Apache Spark is now a very big project, but we're trying to maintain this very central project philosophy that closely resonates with what I discussed earlier, which is we really want to make the life, data scientists, data engineers' life easy and make them more productive. And we do this through a few things. One is we try to maintain a very well-documented expressive API, so you spend less time actually getting confused by the API documentation or even no documentation whatsoever. We built actually very, on top of Spark, we built powerful domain-specific libraries that you can use to actually tailor towards specific analysis. And I'll expand on this later. And then we make it very easy to integrate with existing storage systems. For example, like Hadoop HDFS or Cassandra or HBase. So you can actually directly connect to the data source and load data out from there. And then there's also the one tiny little perk of Spark is you can also leverage the whole cluster's memory to do computation, which sometimes speed up your computation substantially. And last but not least, there's one other thing we're trying to adopt now, which is to do very regular maintenance releases. And we have this very strong high bar for what gets into maintenance releases. Only critical bug fixes gets into them, which means if you're on, for example, 1.0, and you don't have to worry about is upgrading to 1.01 going to break my whole system because it might bring in some external dependency or might change the behavior of some API. Pretty much guaranteeing that's not going to happen. So that makes it actually much easier for people to move from releases to releases. So in the past sort of half a year or so, Spark's really getting a lot of buzz. Starting with maybe at the end of last year, I think at the point already, one of the co-founder and used to be a CEO of Cloudera, Mike Olson, wrote a blog and where he claimed actually the leading candidate for succeeding MapReduce is Apache Spark. And then at about around the same time, at last year's Spark Summit, Eric 14, I couldn't pronounce his last name, but 14 characters. Eric 14, he actually calls himself that. So. Actually said Spark's probably going to become the de facto standard for running machine so data analysis at scale. And earlier, about a month ago, maybe a month and a half ago, Mahal actually decided they're going to stop accepting any contributions on top of Hadoop MapReduce and basically completely move over to Apache Spark. So this actually, Spark has come a long journey since the very beginning, where I believe in 2009, Matej Zaharia, one of the, at the time, a PhD student at the UC Berkeley AmLab, started Spark as a toy project. The first version only had like 600 lines of code. You can still go to GitHub and look it up. It can only do like maps. And basically, it's like a parallel task runner. And then it was first open source in 2010. And in last year, we donated the project to Apache Software Foundation. And sort of about the same time, Databricks sort of incorporated. Matej's currently the CTO. And I think for the first half of this year, almost every major sort of Hadoop data vendors are now announcing or will announce support for Apache Spark. And one of the very sort of historic moment of Spark was the 1.0 release last month, which the biggest change in 1.0 is actually about API stability. So we're guaranteeing sort of a longer term support for the existing API. So you have to worry less about upgrading. So let's get into now the benefits of Spark. Like why are people really excited about it? I think there's a few reasons. The first, which I actually don't think it's as important as some of the other ones, but it's a lot easier. It's much more eye-catchy because when you say it's fast, you give a number and it's very easy to compare. So a lot of algorithms, if you implement it properly in Spark, you can at scale, you can actually run it at scale much faster than what you would get out of Hadoop MapReduce. So this is one example running, for example, logistic regression and k-means on Spark versus comparable implementation on top of MapReduce. Sometimes you get 100 times faster when your data fits in memory. Yeah. But I think more importantly than fast, it's actually probably the latter points. And this includes, for example, part of it is a lot of the high-level advanced DSL libraries we have built on top of Spark. That allows you to do different functionality. For example, you can do SQL directly on top of Spark. You can do data streaming. You can do machine learning. You can do graph computation. And then there's even other sort of more of bleeding edge stuff coming out of the UC Berkeley and some other academic research institutes now. So basically, you can run some very advanced algorithms, and you can run very well different workloads directly on top of Spark. And out of all the 4 points I'm going to talk about, I think the most important one by far is actually easy to use. It is easier to use. And this has a lot of reasons. But one is Spark provides sort of a much nicer programming API to data scientists and data engineers that when you express your workflow or your algorithm in Spark, it actually ends up being a lot more concise. And I'll walk into more details later. And then you have sort of exposed APIs in 3 different programming languages: Scala, Java, and Python. So Spark itself is written in Scala, but there's also sort of other language bindings for it. And then you can actually use Spark. So all of this stuff work across different languages, and you can use a single programming language running in a single program to do a lot of different stuff. This was just part of it is what Aaron's demo is going to be about. And then the last part is it's fully open source. It's actually has become the most active big data open source project in terms of contributor count. So as of February, this is like almost 4 months ago, as of February this year, there's over 120 people that contributed to Spark in the past year. And this number has come up to, I think, probably about like 170 or 180 now. And the total amount of contributors over like 200 to the whole project. And we often get asked also, like, does this thing scale? Like, one really nice thing about Hadoop MapReduce, even though sometimes it's really slow, but it scales and you just let it run, it's going to finish. So I actually just took one of the screenshot from Twitter, a picture from Twitter. Somebody attended the Hadoop Summit for the past 2 days. And this is one of Yahoo's slides where they actually run Spark on over 1,000 nodes. This is a very public referenceable number on the Spark cluster. I know of other clusters that are even bigger than this, but unfortunately I can't disclose them. So let's get maybe a little bit more into sort of what Spark is, how to use it. So Aaron's going to show a demo on top of the thing called Spark Interactive Shell. And it's actually probably the easiest way to experiment with Spark in a local laptop. But essentially, you can run Spark directly on the local laptop. You can just download it on the tarball and start running the command. And then you could also run Spark on a cluster. It supports like Apache Hadoop Yarn, and it supports Apache Mesos for scheduling. You could also set up a Spark cluster without any Hadoop installation, just by running Spark with a standalone scheduler. It supports the different languages. This is giving you sort of a snapshot of what it's like. And then there's a nice interactive shell for both Python and for Scala that you can use. Again, if you just download the tarball, just launch it very easily. It has sort of a fairly nice, clean API that maps, essentially borrows a lot of the essential ideas from functional programming. The core concept in Spark is this thing called resilient distributed data sets, or RDDs. So RDDs is just conceptually a collection of records that's partitioned across a cluster. And then you can create RDDs by pointing RDDs to some external storage file, or apply transformation on RDDs to create new RDDs. And RDDs are fault tolerant, which means if the nodes that have data for some RDD went down, it can so Spark can recover that data automatically. And the two kinds of operations in RDDs is like transformations and actions. And I'll explain them in probably a minute. So if you think about what maybe Hadoop MapReduce gives you, it gives you a very low-level programming abstraction called map and reduce. And this is actually not very natural to program because often your data analysis pipeline doesn't really map to just map and reduce. For example, sometimes it's joining data sets, sometimes maybe you're doing sampling. Even though you could probably use map and reduce to actually express all of those things, it's like fairly hard to shoehorn them. So Spark actually provides over 80 high-level operators directly out on RDDs that you can apply to sort of transform or operate on data. So for example, you could do join out of the box, you could do count, you could do sample, and there's a lot of other functions. So now, using this API, if you were to write the canonical example of big data, which is just counting how many times each word appears, word count. I have no idea why it's the hello world of big data. But so on your left, there's Hadoop MapReduce version of word count, which you probably can't really read. But I can tell this is basically just a map class and a reduce class from word count without any of the import statements. And then on the right, the Spark version of it, which is probably still too small for you to read, so I can expand it. So basically in about like 5 or 6 lines of code, you actually run word count very efficiently, distributed across a cluster. Now, I'm going to go RDDs by just pointing out, referencing some external storage. And then there's transformations, which gets applied, essentially what we call coarse-grained transformations on RDDs. And what there's a lot of different transformations. Most of the operators I showed you earlier are transformation, like sample, filter, and all of those. So in this case, this is actually using the Python API, where let's say if we have an RDD created for a text file, and now I can apply a filter transformation. And what filter does is it accepts a lambda function, an anonymous function in Python. And for each line, it's going to run the anonymous function. If the anonymous function returns true for that line, that record gets basically in alliance with Spark RDD. If it doesn't return true, it gets filtered out. And then there's another kind of operation in RDD called actions. And what actions does is essentially actions don't create RDDs. Actions actually return some result. This is a very minor distinction, but it's going to be very important. So I'll explain in a little bit. So essentially with actions, for example, count, this is just returns on how many elements are there in this RDD. Or you could do, for example, first, which returns the very first element. There's a lot of other actions. You can look up the API documentation yourself. Now, this is still a little bit ambiguous. So I'm going to walk through sort of an example on log mining a bit. But now, back to the difference, really, between transformations and actions. So transformations return RDDs, and actions actually return some sort of result to the user. And what this means is Spark could actually exploit the fact that transformation return RDD. And RDD is really just a conceptual idea in Spark. It's basically an interface that you define. And it doesn't, so it means RDDs don't have to be materialized when it's created. And what this means is you actually apply a lot of the sort of higher level optimization, such as pipelining and all of those. So now let's walk through an example which explains this better. So the example is very simple. It's just doing some log mining, doing like distributed grep in a way. And in here, I have a small Spark cluster of 4 nodes, and very similar to sort of how Hadoop MapReduce and a lot of our distributed systems are designed. You have a driver node, which is responsible mainly for metadata tracking and for scheduling. And you have like 3 worker nodes that's actually responsible for the real computation. So in this case, let's say we're just pointing, again, now create a lines that points to some logs on HDFS. And so we're creating an RDD. And then let's say our production logs, I'm debugging some production issue, and I'm really only interested in seeing error logs. So in this case, all the error logs, line actually start with the word error. So I'm going to apply a filter operation, filter transformation on the lines RDD to create the errors RDD. And the filter itself is very simple. It's just a lambda function that checks whether the line starts with error. And then let's say my log messages are tab delimited, and I'm only interested in really the third field. Maybe that's what the error message is really about. Now what you can do is just apply now a map function. Essentially what a map function does is for every element in the errors RDD, it's going to apply that lambda function, anonymous function, on that line, and then put it in the messages RDD. So in this case, the lambda function is very simple. I take in the string, which is the whole line, and I split it by tab, and I take the third field out of it. And then next, let's say I know I'm going to be repeatedly querying this messages. You could actually give Spark a hint called .cache to put this messages RDD into memory across a cluster. Now, going back to sort of transformations, because remember, lines, errors, messages are just RDDs. RDD is really just some sort of logical concept in Spark. It doesn't have to be materialized. So actually, what we have done so far are just metadata operations on the driver to tell Spark, how do you create lines, how do you create errors, and how do you create messages? And this is the concept called lineage. Essentially, how do you create each of the RDD? That's the lineage information the driver is tracking. And now let's say I want to count how many times the word MySQL appears in my log, error log. Now I can apply, again, just a filter transformation and apply an action called count. Now, action is the one, count is the one that actually returns an integer. So we cannot be sort of lazy or don't materialize the data anymore. We actually need to do the counting. So in this case, the Spark scheduler is going to actually query, it's going to figure out the way I can get a count is by computing messages, and the way I compute messages by computing errors, and the way I compute errors is by computing lines, and lines actually point to stuff on HDFS. So scheduler is now going to query the HDFS name node to get how many blocks are there on each of the, for this data set, and then where they are. And then the driver is going to dispatch the tasks to actually execute them. So now it's going to send the task, and each task is going to read from the HDFS on this block. And then because we mark messages as sort of try to put it in memory, each of the worker, while it's executing the task, it's going to build up this in-memory buffer for each of the block, just for messages. And then it's going to return the result. And the driver node is going to be doing the final aggregation of the count. So now, let's say you're okay. So now let's say MySQL, you've saw all the error messages related to MySQL. Maybe now we want to see how many error messages are that's related to PHP. So it's probably a very outdated web shop. But now, so you could just essentially replace the MySQL keyword with PHP and then run the same query again. Now, but this time, because we already have the in-memory blocks of data, when the driver is dispatching tasks, it's going to schedule for the in-memory locality. In this case, it's probably going to be on the same node anyway. And then each of the tasks is going to read directly just from the in-memory cache. Now, it can end up being a lot faster. So, this depends on, so it depends on your workload, right? If you're doing raw byte copy, you essentially get how fast you can do memory copy in the JVM versus reading from disk. So you're talking about like 2 or 3 orders of magnitude. But if you're doing computation, if your computation is light, you could easily get about like a 2 order of magnitude difference. If you're extremely CPU bound, maybe you might not see any difference. Does that make sense? It's very workload dependent. Yes. It wrote the memory and then return the data. Yeah. So it load in. So if you don't have the cache, it's gonna stream through the whole thing. It's gonna process it essentially line by line, and then you don't really have any like buffer build up. But if you have a dot cache and Spark's trying to build up in memory, it's gonna build essentially messages in memory and then return the data. Yes. Yeah. So if one of them fails, you do have to rebuild them, essentially with the lineage idea. Now, one of the nice thing about the lineage idea is because usually when you run on a real thing, you typically have a lot more blocks in the machines. So for example, on one of your machine, you might have, let's say you have 10 blocks. Now you can actually parallelize the recovery of those 10 blocks across your rest of your cluster. So recovery can actually be pretty fast. Yeah, maybe last one and then I'll move on. Yeah. Yeah, so there's so cache is synonym for persist, and there's an unpersist call that you can. essentially get rid of stuff in memory. There's definitely no guarantee everything's going to be in memory always, because you might just start caching stuff that's bigger than the amount of memory available. This eviction policy, essentially right now, is just a block level LRU that can evict data. So I'm going to skip this. So now, I think I covered sort of a very introductory level, sort of how you would program Spark. But now let's maybe talk about a little bit of high-level libraries, and then Aaron's going to do the demo, which you get a more realistic feel of what it's like. So we built up, I think right now there's 4 essential libraries on top of Spark, along with the Spark 1.0 release. This is Spark Streaming, and this Spark SQL, there's a machine learning library, and then it's GraphX for graph computation. I think the names are pretty self-evident on what they do. But essentially, let's walk through them one by one. But essentially, the core idea of all this libraries is in Spark Core, we provide the essentials to the programming abstraction called RDDs, which is essentially just distributed data sets, along with transformation and all of them. And then on top of them, we have designed all these high-level libraries that actually map very nicely to distributed collections. So for example, in the case of streaming, essentially what you get is time-sliced distributed collections. So you have a stream of data coming in, essentially chop that stream into small slices, and each slice becomes one RDD, and you apply transformations on it. And you have SQL, which essentially is RDDs with schema. And then you have machine learning libraries, which is essentially just RDDs of vectors and matrices. And you have graphs, which again is RDD-based graphs, which under the hood actually just turns, each graph becomes 2 RDDs. It's an RDD of vertices and RDD of edges. So in the case of Spark streaming, one thing we realized is Spark, in the very beginning, even though it's like a lot faster than say Hadoop MapReduce, it can probably process some kind of data in probably in the range of seconds. But a lot of people really want a higher level programming abstraction when they're programming against data streams. Like at some point, you can probably view the whole world, any data, as streams. So we built essentially a DSL or library for streaming. What it does is, again, as I said earlier, let's say you have a stream of input. The way you do it, still the slide from Aaron, that's why he's laughing. So we actually chop the stream into slices. And then each slice is represented by one RDD. And then you can apply essentially your MapReduce or even window functions against this. Do you have a question at the end? Okay. Yeah. What's the name of the grid game? Yeah. So I don't know. Maybe I'll answer that question after this slide. Yeah. It's a very good question. So essentially, you can create a stream, and then you can apply RDD transformation on the stream. And the really nice thing about it is now, if you think about historically, the way you program like complex event processing systems or streaming systems, they have a very different programming abstraction from your batch systems. And what usually end up happening is in every single company, I've seen this pattern over and over again. You implement maybe say your fraud detection or outlier detection algorithm for the streaming system, and you implement the same thing for your batch system. And you're gonna run them and maintain 2 different code bases. Versus now, actually in the Spark streaming concept, because everything under the hood is really just based on RDDs, you have a single programming abstraction that applies for both streaming data and for batch data or historic data. And now you can write your program once and apply it in both settings. And this actually becomes incredibly powerful because you don't have to worry about maintaining 2 code bases, writing 2 test suites and all those. Now, in Spark 1.0, we added actually a new, so I wrote Shark during my PhD, and now we're actually phasing out Shark. In a way, it's killing my own baby. But we've been working on this new thing called Spark SQL. Again, that's directly built into Spark. In Spark 1.0, Spark SQL is released as an alpha component, and we have actually a lot of activity now going on in Spark SQL in the next few months. Essentially, Spark SQL exposes RDD of schema rows, schema-aware rows, and we have made it in a way because we're using a lot of like the more advanced SQL and Scala Scala language features to actually blend the line between what SQL can do and what a Spark programming language can do. So often, if you think about it, a lot of people are really often when in your exploratory data analysis, maybe what you really want is just some sort of SQL query aggregations, maybe joining some different data sources. That's a lot easier to be expressed in SQL. But as you get more advanced, it gets incredibly frustrating to actually program in SQL because you could try, for example, even writing PageRank in SQL, but very few people in this world can understand how that SQL statement works. Sometimes it gets like pages of SQLs. So essentially Spark SQL, because data under the hood and the execution engine of Spark SQL is really just RDD transformations, you could get RDDs directly out of SQL execution and then apply Spark-like transformation directly on those results. So let's, for example, you might be able to use your SQL to select subset of the data, which now can still be pretty big, spread it across a cluster. And then you can maybe apply, for example, k-means or logistic regression directly on top of that. And there's actually two ways to program Spark SQL. One is just vanilla SQL. And the other one is we also created a DSL that essentially allow you to construct SQL query plans using this DSL programmably. And the last one I'm going to talk about, which is maybe a lot of people, because of the data mining groups, very excited about, which I think is slowly becoming the de facto standard for running a large-scale machine learning, which is machine learning library on top of Spark. So I'm not a machine learning guy. I don't know enough math to back up my slides. So please don't ask me how maybe, let's say, ALS works. So the idea of MLlib on top of Spark, as the name indicates, is a machine learning library on top of Spark. Essentially, it's just an RDD of vectors or matrices along with implementation of algorithms. So we have a lot of people actually implementing very high-quality algorithms for distributed algorithms on top of Spark and putting them into MLlib. And right now, in the Spark 1.0 release, this is all the sort of functions that's available right now. And the nice thing about using MLlib is because it's really written by experts, and it's very carefully code reviewed and pretty well documented. You don't really have to worry about, is this going to scale? You can actually run this code on a single node, and then you could scale it out to maybe tens and hundreds of thousands of nodes later. So with all these DSLs, what does it mean for the user? Maybe you could actually find comparable sort of libraries for different systems out there, or maybe use different systems for them. Really, for the benefits for users now, you can actually use a single programming paradigm, a single programming abstraction to cover your data sort of analysis pipeline from the very beginning of getting data, cleaning data, to exploring data, and to maybe building models, and to real-time serving models at the end. You can cover it from end to end. And your application can now compose different programming models on top of this. For example, running SQL, and then for the results that you selected from SQL, run a machine learning algorithm on it. And then because we can actually, all of this share the common core, improvements to any of this actually improves all the other systems in a way. So there's a lot of my
Okay, so the plan is we're going to start with Twitter data. We're going to, like, say, an HDFS or something. We have raw JSON tweets, so they're structured. And we're going to bring that directly into SQL and query it as a table. After that, we'll take it into machine learning, into MLlib, and do some machine learning on it. As the premise for this is that every tweet has associated with it a language, but we suspect that maybe this language isn't correct always. Maybe if you just log in from the browser, it defaults to English. And so what we're going to do is we're going to actually build a machine learning classifier for languages to actually classify tweets based on language. And we're going to take that model that we build here, and we're going to do a streaming analysis on this using live Twitter data. So we're going to take live Twitter data and classify it based on the language. Okay. So, oops, haven't done it yet. Let's do it. Candidate. All right. 1 second. Sorry, I need to. I'm going to leave a little room at the top, at the bottom, just to make sure that everyone can see it, so it's not too low. Okay. All And this is kind of annoying, so let me go that. Also kind of annoying. OK, cool. Now let me try to put this here. It does work. All right, so here I'm on a remote cluster. There are a total of 10 machines here. So Reynold said you could use the shell locally, but I'm actually using it now to connect to a larger cluster. So I'm running this thing called the Spark shell. And this is basically an interactive session now. You can also run jobs, but this is interactive. It has a cool ASCII art. That's always a bonus. And this is actually Scala. So I can do normal Scala things like x, and I can add x plus 3, and indeed it is 8. And then, so now let's do more cool, let's do Spark things. So let's take our tweets. So I'm going to take a text file, read it from HDFS, tweets, and let's see what that looks like. I'm going to take the first element, and we see that this is, in fact, a tweet, and it is also in Japanese, so I don't really know what it says. OK, a couple of things to note before I go further. One, these tweets are often selected at random, so hopefully none of them are too insulting. Second, feel free to ask questions during the course of this as it goes. OK. So this is, as I said, JSON, but maybe you don't believe me. So I'm actually going to import this little function. This is in Jackson, so you can see it's actually a lot of code. The whole point of this, in fact, is simply to pretty print a JSON string. So much code for that. I'm going to take my tweets.first and pretty print it. And here we go. As you can see, it is actually JSON, which is now nicely delimited. We can see that it has text. This is the actual tweet. It has some entities. It would have like the retweet who retweeted it. ID has username. Here's the user. And it's very nested. OK. So what we're going to do now is we're going to bring this into an SQL table. Sorry, not SQL. I've done that before. So we're going to import SQL. We're going to make a new SQL context, which just wraps a Spark context and adds new functionality. So let's see. OK. And now I'm going to make my tweet table by using this cool function called JSON table from RDD, context tweets. OK. And before I run this, let me just tell you what I'm going to do here. All this text is non. Sorry. OK, there. It just annoyed me. I'm sorry. OK. So what this is going to do is this is going to read my JSON data from my RDD of strings, and it is going to determine the schema of this data. Because fundamentally, this JSON data is very structured. It has a schema underlying it. Not all JSON data does. Sometimes it changes very quickly. But this, overall, the tweets have a fundamental schema. So this will detect it. This sum at the end, sum 0.1, means we're going to sample 10% of tweets and take the union of all of their schemas. And this is actually running on a cluster. One thing to know about this code is it's actually not in Spark yet. It will soon be in Spark. It's just like, it's really cool, so I just wanted to get it hot off the press. All right, so now what we see is we have our table. Let me just show the schema. And indeed, this is like a real schema. We can see that it's also inferred some of the types, like was it favorited as a Boolean, and it's just fully nested. And I can do RDD things. Reynold alluded to this. It is an RDD, so I can do RDD things. Here is my tweet. This is not the same one, I don't think. Or maybe it is, actually. Oh, yeah, you're right. Sorry, it is the same one. But this is actually a row object now, not a string. And you can see we've inserted some nulls here because we expected something to be there. Now I'm going to start the magic. So I'm going to register as table. I'll call it tweet table. And now I can do SQL on it. So for instance, select text from tweet table, limit 10. This is the result of this is also an RDD. So I need to collect all the results on the driver, and then print them each line. So now we have 10 different tweets. In different languages. We see Arabic, we see English, we see more Japanese. Cool. So let me just show you that this isn't like fake or anything. I can also print like the username, the text, and the language, and it's fully nested in SQL. It's very natural. And here's another 10 tweets. And you can see here that, let's say this Korean one, we have like the username here. It's not very prettily printed. It's just like an array each row. The name, the tweet, and then the language, Korean. Okay. So let's also do a little bit better analysis. Let's try to find how many tweets are associated with every language. So I'm going to select language and the count as count from tweet table, group by lang, order by count descendant. Okay. So this will now actually run over all of the data, so it's going to take a little bit of time. And it will group by language and find the count, and we'll get the top 10 results. Question? Oh, yeah. How much is the total data set? The total data set is 60 gigabytes of tweets. And later on, we'll see it's actually 12 million individual tweets. And there are 10 machines here on EC2. Sorry, the sampling, 60 gigs before the sampling was only to determine the schema. This is actually operating over the whole thing, which is 60 gigabytes. OK, so we found the result. And we see that there are 4 million English tweets, 1.8 million Japanese tweets, 1.5 million Spanish tweets. Cool. But maybe, as I said, I don't necessarily believe these numbers, and maybe I think that they're not fully categorized correctly. So now let's go to machine learning. So I'm going to just select the text from tweet table. And this is just an RDD, so I'm going to call it text. And I can take the first one, for instance. One thing to note here is that the type of this is actually row. It's not string, because it's returned from this RDD. So I'm going to go over every element, take the first column, which is just the only column, and convert it to string. And now this is just, the type is a string. OK, that was just some conversion. All right, now the machine learning magic. Yes. Yes. Yes, by default it does. I've actually turned off some of the more expressive logging, just because and I can also, yeah, that should be here. We also have a web UI where you can also see historical runs. Here was our, we do have a job server. This is just anytime you run a shell or a job, it starts this by default. And so we can see how that ran. OK, also running jobs. OK, let me import this machine learning stuff. So what this is, I've imported this and had a couple other imports. All this does is it takes my tweet and converts it to a vector, a feature vector. To those who are not so familiar with machine learning, such as me, what this basically means is we're taking our tweet and we're making a mathematical representation of it so that we can more easily operate over it on it with these various algorithms. And so what we're going to do here is we're going to take these tweets, convert them to math, and then cluster them into 10 different groups. And that hopefully will be 10 different languages approximately. OK, let's just see what does featureize look like. So I say featureize hello world. And indeed, that is a vector. It looks perfectly reasonable as a vector for hello world. And now I can just say take my tweet, my text, apply this featureize function to every single one of them. Again, it's lazy, as Reynold alluded to before. And let's get the first one. That's another perfectly reasonable vector. Now I'm going to cache this and count it. The count serves two purposes. One, we'll see how many tweets we actually have, although I already told you. The second thing is this will actually force the data to get into memory because the cache is lazy. So once I say count, and let's just see it executing, you can see it's counting. And we can also see like the tasks. So as this executes, it's actually storing the RDD in memory. This is the storage tab. It shows what RDDs are in memory. We see that 31% of this RDD is in memory at only 2.4 gigs. By the way, this is much smaller than the original 60 gigabytes because we only took out a text and then turned it into a vector. And we can see that number going up. OK, so once this count is done, hopefully, because I have enough memory, all these vectors will be in memory. Any questions at this point? This will take only a little longer. What type of machines the cluster has? These are M3 2x large. That means 8 cores and a good amount of memory. I'm not using nearly all of it. The question was, are we using the SSDs on these guys? No, we're just using EBS. Yeah, I didn't really optimize this. Mostly because the interesting part is once it's in memory. So now we see that there's 12 million tweets, and it's extremely, so when I say count again, it is actually doing the entire job. Okay, so rather than reading from HDFS, it is actually reading just straight from memory. Okay. Just one more time to make sure it didn't change. You never know. Oh, sorry, I don't need to go back there yet. Oops. Okay, so now I'm going to train my model. k-means.train vectors with 10 cluster centers and a max number of iterations of 10. So this is going to run like it's a full-blown machine learning model. It has to like go out, do computation, bring it back in, and repeat. As I said, there's going to be 10 different clusters, and the max iterations of 10 means that we're going to go over it 10 times, pretty simply, unless it converges, which it won't. The really cool thing here that we see here is this iteration. For machine learning, it's extremely important to have this data cached in memory. In fact, I was doing this practice talk, I was just practicing, and after 2 minutes, I forgot to cache my vectors, is what I mean. And after 2 minutes, it hadn't gotten through the first iteration. And now we see here it's already gotten through all 10. So it's very, very important that you get this caching model, that you can keep this in memory over each iteration. All right, so now we have our model. And let me just show you. Let me take some tweets. Equals text, take 100. So I take 100 tweets. And now all I'm going to do, I've already done it, is take each tweet and see which cluster it should be a part of. All right. So cluster 0 seems to be, there's only one tweet. I don't know what cluster that is. Cluster 1, well, it has, actually this is a pretty wide spread of languages. That's not a very good cluster. Cluster 2, by the way, so this is totally randomly. Sometimes the clusters come out great, sometimes they come out a little less. This one seems to have some Spanish, I guess. Yeah, a good amount of Spanish. Yeah, okay, cool. And Portuguese, yeah. Oftentimes it groups Spanish and Portuguese, sometimes French in there. I can understand why. I can't tell the difference always. Cluster 5 looks like Arabic. That looks pretty cool. Cluster 6 is actually an interesting cluster. I'm not sure if you guys can see what all these have in common, but they all have URLs, t.co URLs. That's apparently a language of its own. Question? Why are there some? Oh, so yeah, the k-means clusters, none of the clusters should be empty. The thing is, I took a random 100 tweets and said, which of these should it be in? And so some of the clusters are definitely smaller, and of the tweets I took, none of them matched that cluster. Okay, so there's Arabic, there's some URLs, there's, I guess, English. Cool. So let's pick, for instance, Arabic, because that one looks cool, and if there's insults in there, most of us can't tell. That's number 5. So we're going to make RDD. What I'm going to do now is I'm going to save my model to disk. So cluster centers, save as object file to HDFS. Hope this works. And it worked. Okay. Now we're going to go to streaming. So we have our model, and I want to, in real time, use this model to classify tweets. So let me just, all this does is run a thing called clustering demo. It takes in the model file I generated before, and I'm doing cluster 5, which is hopefully Arabic. So hopefully you'll see a bunch of Arabic tweets once this gets initialized. And I'm going to show you the whole program that this is once it gets started. Okay. It'll take just a couple seconds to get started. Any questions? No? Okay. Okay, so I hope. Yeah. When I saved the model to disk, which is just a vector, it's a bunch of vectors. It's the cluster centers. All right, so here we see successfully we are reading live tweets, and we are using our model to classify and say if it's Arabic, print it out, and it seems to be working. Cool. And let me just show you the entire program. Oh, let me make sure that. Oh no, I forgot to make it big. Well, this isn't very useful then, but I guess I can just kind of tell you what it is. This is the entire program. First, we construct a streaming context, which is the same thing as a SQL context. It just wraps a Spark context. We load our k-means model from disk. We create a Twitter stream, which is very easy. We find just the text, and we model. We predict which cluster that text should fit in, and if it matches number 5, Arabic in the previous example, then it prints out that model. It prints out that text, that tweet. And here we see this. Don't show you the secret things. Those are just my Twitter auth keys, which I've happened to have hard-coded to make it easier on myself. This is the featureized function. And this is the same exact function I printed into the shell. You can see it's like very easy to reuse code because everything's running on the same stuff. Okay. Okay, so let me just wrap up. Now I can show this, what we did. We did successfully take our raw JSON tweets. We took them into an SQL table. We immediately, straight from SQL, We converted them into machine learning in the same program, and then we took that and did streaming, did a machine learning model on that, and clustered, classified our tweets in real time. Here is all of the code again. This is all the code we wrote, plus including the streaming code, and that was very simple. So, okay, so this is actually, these slides are actually from my Hadoop deck, so I will let Reynold give his version of these slides.
Yeah. Hello. Do I need to repeat my answer? I'm gonna take it as good. Yeah, the question was, what if you don't use cache? Like, what happens? You go back to disk, but often you can still end up being a lot faster because of like faster scheduling, because of better sort of optimization of execution plan, for a lot of reasons. I can talk more offline and explain it. Yeah. Yeah. So essentially, you can run arbitrary user code. And so now it's up to the user how you want to integrate with your favorite library. Like for example, the machine learning library, MLlib and Spark, interface with like native BLAS implementations through the Java native interface. And you could also run PySpark, which is a Python API for Spark. And then because it just runs, I think, Python, am I right? Yeah, and then you could actually connect to all the native libraries implemented for Java, for example, NumPy and all of those. Sorry, Python, like NumPy. Or even run scikit-learn. Like I've seen people launching a Spark job to parallelize actually scikit-learn model training. So they train a slightly different model on each node and then aggregate to pick the best model. Yeah. How do you distribute? Yeah, it's a very good question. How do you distribute the code base? So there's multiple ways. One, you could open the SSH terminal and start rsyncing. Just kidding. But that's actually it's one good way to do it. The other way is when you have a Spark context, you can actually call .@jar or @file, and it's going to distribute the data, the files, over to all the nodes. Yeah. So Spark provides essentially there's one native join interface, which is essentially triggers. It's similar to the way you do MapReduce joins. So you have two input sources, and you do a shuffle. So you essentially repartition the data with the same partitioner, and then on each of the once the data are partitioned, you read from both sources, and then you compute a Cartesian product on what? Not exact Cartesian product. You put stuff into the hash table. It's like a hash join, and then you compute Cartesian product for the values having the same key. Now, you could also easily implement a broadcast join if one of the table is small. So this is when you're joining a large table and a small table. The easier way to do the join, a much less expensive way to do the join, is to broadcast the small table. So Spark has a different implementation of broadcast mechanism in Spark, including, I think the default one's like just very TP, but there's also a BitTorrent implementation that you could actually torrent your table across, which is probably the most efficient way of doing broadcasting. Yeah. How production ready is the HBase RDD? There's actually no magic there. It's essentially just using the HDFS. So essentially think of it, it's running user level code. And the way it works is HBase has a Hadoop input format, and we just run that code. So the nice thing about the Spark design is it actually interprets very well with Hadoop and then the Hadoop ecosystem. So it's very easy to reuse all the existing things. Yeah. Yeah. Yep. Yeah, so the question is what happens in in failures when let's say you have a 100 node cluster and one node dies, what happens? So a few things, right? One is, so Spark, essentially the RDDs have lineage information, how to reconstruct them. So essentially, let's say you have 10 blocks in that node that died. Now, Spark can use the lineage information for those 10 blocks and now reconstruct them on the rest of the, let's say, 99 nodes. Or you do really need at most 10 nodes to run them, because you only have 10 blocks to reconstruct. So essentially, you're going to keep going back to the way where somewhere there's a stable storage. Like, for example, maybe you have 3 copies of each block in HDFS, so you can read from the 2 other copies, and then to reconstruct on other nodes. Yeah, was it? Yeah. So Spark itself, the question is about what's the best file system to write out for persistent storage. So a lot of people use HDFS because there's sort of native support for it. But Spark is sort of designed in a way it's a file system agnostic. So for example, you could write to like MapR file system. I know people writing to like Ceph. There's also some in-memory file system in Berkeley developed called Tachyon you can write it to. Or I know there's people there's getting actually more and more people running Spark outside of the Hadoop ecosystem. For example, writing directly to Cassandra and all of those. So it is very sort of implementation, file system agnostic. You can have different implementations you want to write. Essentially, you can run any arbitrary user code. Spark itself doesn't come with its own sort of persistence, yeah. It's more of a computation engine. All right. Should we, oh, sorry, I never turned my. Oh yeah, what happens if a driver goes down? That's a very good question. So there are, do you want to answer that? You implemented it. Yeah, but then you can submit the driver. You can talk about 3 minutes. Okay, I'm gonna let Aaron talk about this since he implemented a pretty cool feature.
Okay, I just reviewed that feature. Not quite the same thing. Well, so one thing is that if you don't do anything, what's going to happen is your job's going to stop because it's like the driver program. It's like if my Spark shell dies, then yes, things are going to stop. But we also have a feature now in Spark called deploy mode, where you deploy your driver into the cluster, and then if it dies, it'll just be restarted. And so you can implement your own code on top of that. It's a very, very simple interface. It just restarts your driver. You can implement your own code to say, well, if I already have partial results, just pick up where I left off. And that's it. It just runs inside the cluster. What do you mean by metadata? Yes, that is lost by default. However, we have other like Tachyon, which was mentioned earlier, which is in-memory file system. For long-running jobs, it's great to write your data to Tachyon. That way, you can just read it directly back in without ever actually going to disk. In the case of a driver failure.
To add on to that, so one of the things is the driver is actually just a user-level program that the user can run arbitrary things in the driver. This is very different from like the MapReduce, like the application master, the job tracker. It has both the metadata and user-level logic. So it's actually at some point also up to the user to code in the way. So Spark provides you some basic mechanism of how to recover it, but it's also up to the user on what to do once you recover. Yeah. Should we just break off and? All right. Well, thanks for coming. We're gonna hang around here for a little bit and.